Okay, hello, how are you doing? So we are done with your quiz. I will try to grade it over the weekend and I post your result and okay and the solution to your quiz. So what I'm going to do is I'm going to review, give you an idea from this section 4.5, which is very important section. It's very important. It's very tricky. And to solve the problems, you need some kind of special methods that I'm going to talk about it. You get quite a lot from this section, so read it carefully. I try to give you all the possible examples, so then you'll be fine. Okay, so we are going to talk about the dimension of a vector space. Okay, so let me go to my notebook and explain it. What's going on in this one? Okay. So this is it as usual. We have to wait to take care of this camera. Yeah, that's it. So it will be fine in a minute. So we can get the focus this one. Let's try once more. That should give us a better resolution. Yes, that's it. Okay, so it's going to be a great section. You need help to understand the concept of this section. So what's going to be this section about is the dimension of a vector space. Okay, so it's a 4.4.5, and we want to know what is going to be the dimension. Okay, the dimension of a dimension of a vector space Now, when it's a Euclidean space R2, R3, we usually talk about the dimension, but we haven't defined it. So what do you mean by the dimension? So what we're going to use to do is we are going to use a basis for defining the dimension of a vector space. We already talked about the basis. You know that it's going to be a collection of vectors, independent, that expand your space. The number of the vectors in all the bases of a given vector space are going to be the same. We did this one before. So since the number of the vectors in all the bases are going to be the same, that same number is going to be taken as a dimension of a vector space. Okay, so just remind you that we use, okay, that's going to be the number that we're going to use. So we are going to use the number of, okay, the number of vectors in a basis. Vectors in a basis, okay, for the dimension, okay, for number of the vectors in a basis, okay, for its dimension of the vector space, if you like. Okay, so for example, since in the case of the the standard base, the standard, okay, standard basis for R2 and R3. You know that for R2 you have ijk. So in this case, the first one have two vectors. Okay, the first one have two, and the second one have three. Okay, it's three vectors. Okay, three vectors respectively. Okay, respectively So then we say that the R2 is a two-dimensional. R2 is a two-dimensional. Okay, it's going to be a two-dimensional. And R3, three-dimensional. And R3 is a, okay, is a three-dimensional, three-dimensional, okay, vector spaces, vector spaces. So if you can find a basis for a vector space, okay, a basis for the vector space, then you count the number of the vectors in the base. So that number of the vectors in the base is going to be the dimension of your space. So officially, this is going to be the definition, okay? Officially, this is going to be a definition of the, okay, of a dimension. If a vector space, okay, if a vector space V, okay, has a basis with n elements, okay, a basis consisting, okay, a basis consisting, okay, consisting of n vectors, okay, n vectors, then this n is going to be dimension, then the dimension, okay, then the dimension of this space, okay, dimension of V is going to be, is set to be n. So the dimension of a vector space is the number of the, it's going to be the number of the vectors in a base, okay? Dimension is going to be n. The dimension is going to be denoted by, okay? It is denoted by, the notation is going to be denoted by n equal to the dimension, okay? Dimension of V. Okay, dimension of V, and V is going to be called, in this case, n-dimensional. And V is going to be called, okay, this is called a n-dimensional or a finite dimensional vector space. A finite, okay, finite dimensional vector space. Vector, okay, vector space. This is going to be a situation that we are going to have. Okay, so it depends how many vectors are you going to have in your, okay, how many vectors you are going to have in your base. That number would determine, okay, that number would determine the dimension of your vector. Okay, I'm sorry. This one. Okay, so it's going to be finite dimensional. In specific cases, you know that if you have a vector space that contains only 0, you need to have the 0. Okay, if it's going to be containing the 0, then we say that in this case the dimension is 0. Then the dimension, okay, of this vector space is going to be equal to the 0 dimensional. So if you have one more vector, then in that case you are going to have the one-dimensional one. Now, this example is very important. Okay, so you can use the idea of this example anytime you want. Okay, and we're going to use it quite a lot. The first one. The first case is that if you have, you see, if your vector space is the finite dimensional Euclidean space. If this is going to be, okay, if this is going to be Rn. Remember the Rn? So we can have a basis with a standard base when you move those ones. So in this case, the dimension, since we can have a basis with an element, So the dimension of Rn, okay, dimension of V or Rn is going to be equal to, okay, dimension of V is going to be equal to the n. So that is why Rn is called n-dimensional Euclidean space. Okay, so we can use it from now on. R3 is 3, R2 is 2. So that's going to be case 1. Okay, you can use it anytime you like. What's going to be case 2? The case 2 is if, okay, if you consider the vector space of Pn. Remember the Pn? Pn is the vector space of all polynomials whose degree is going to be at most n. At most n, you know that if this is going to be the case, then we have a basis. Then, remember, then if you have this basis, the polynomial would be a combination of 1, x squared up to the, okay, up to the xn. And you count these elements, we go up to the n. So there are n plus 1 vectors in the base. So then this is going to be a basis, is going to be a basis for Pn. So the dimension of the Pn, okay, so the dimension of this vector space, or dimension of Pn, if you like, is going to be equal to the, okay, is equal to the n plus 1. Okay, it's very popular and we're going to use it quite a lot. So if you get a P2, the dimension is going to be 3. Okay, if you get a P2, the dimension 3, P4 is going to be 5. So you can use it anytime you like. Okay, so the Rn is n-dimensional. If you get a Pn, the dimension is n plus 1. Okay, we use it freely, and that is going to be the case. So if you claim that the dimension is n plus 1, you should give us a basis that contains n plus 1 vectors. So that's why. That is number 2. The other popular one is going to be, as usual, you see we have 3 examples. Example of the vectors, examples of polynomials, and of course, example of matrices. So if you have V equal to, okay, vector space of all M by N matrices, remember, M of M times N. So this is going to be a vector space of all, okay, vector space of all all M by N matrices. If this is going to be the case, then the dimension is, okay, if this is going to be the case, then the dimension of this space, okay, the dimension of this space, d of V, is equal to the M times N. M times N, you can use it anytime you like. Okay, so for example, just to show you how you are going to prove it or just claim it. For example, if V is going to be the space of, okay, vector space of all 2 by 2 matrices, then if you claim that the dimension is 2 times 2, which is 4, you must provide a basis. Okay, if this is going to be the case, you say, oh, then I can give you a basis. So what's going to be a basis for all 2 by 2? We already talked about this one. So the matrix is going to be 1, 0, 0. This is one vector. Okay, then you move the 1, 0, 1, 0, 0, and then 0, 0, 1, 0, and lastly 0, 0, 0, 1. Okay, you know that this is going to be a basis for the vector space of all 2 by 2 matrices. Okay, so is a basis for, okay, for M 2 by 2. And as you can see in this basis, we have 4 elements, 1, 2, 3, 4. So the dimension is 4, M times N. Okay, so this is going to be the case. So the dimension of your vector space is going to be equal to the 4. So anytime you claim the dimension, you have to give us a basis. Okay, again, you can use this one anytime you like. So this is going to be the third case. Now, what is going to be the fourth one? The fourth one is going to be the case that you see if you consider a subspace. Okay, if you consider a subspace, you see in general, if W is going to be a subspace, okay, it's going to be a subspace of a vector space, okay, of a vector space V, then it can be easily shown that then the dimension of the smaller one is always less than equal to the dimension of the bigger one. Okay, so the subspace, you know that when you consider the bases are going to be less than the basis of the V. Okay, it may be equal, but it cannot be greater than. So that's why the dimension of the subspace is always less than equal to the dimension of the full space that we're going to have. Okay, so that is we can use it as a conclusion. This would be interesting. Okay, if you consider W, if W is going to be, if W is a subspace, okay, it's going to be a subspace of R3, okay, it's going to be subspace of R3. You know that the dimension of the W must be less than the dimension of R3. So then the dimension of W is going to be less than or equal to 3. Dimension is an integer, so this means, so the possibilities are dimension of W can be equal to 1, 0, 1, 2, and 3. So these are the only possibility that you are going to have. Okay, if this is going to be the case that that you get only, you see, if this is it. So in the case of the, let's consider, say A, if the dimension of W is equal to the 0, so this means that W would contain only 0 vector. Okay, this is going to be the one. If the dimension happen to be equal to 1, okay, if the dimension is going to be equal to the 1, then geometrically, if you like, the W is just going to be a line. W is going to be a line. Okay, it's going to be a line through the origin. A line through the, okay, through the origin. You know that the line through the origin, the equation of a line through the origin would be what? Would be, so this is it. You see the W is going to be the set of all the members like XX, when X is a number. X is a number. Okay, because the equation of the line through the origin is this one, for example. You make it, you get X, 2X, 3X, 4X. So this is going to be the case. Okay, we get the X and the 2X, 3X, 5X. It doesn't matter. So as you can see, the basis is going to be just one element. Okay, and then you can continue taking, if the dimension is 2, okay, if the dimension of that subspace is equal to the 2, so this is going to be, W would be a plane through the origin, is a plane in two-dimensional. Plane, okay, through the origin, okay, it's going to be the case. And in the case that the dimension is equal to the 3, Okay, if dimension is equal to 3, you know that this must be the space, the full space. So in that case, W is the same as R3, three-dimensional space. Okay, so to give you an idea, you know, it's going to be good to know that if you have a subspace, the dimension of a subspace is less than or equal to the dimension of the full space. So in this case, you see the space is a three-dimensional, so your subspace dimension would be 0, 1, 2, 3, you know, and we can give a descriptive for this one. Okay, so that gives an idea of what is the meaning of the dimension, is the number of the vectors that are going to be on your, okay, in your basis. Now, if we know the dimension, then that would make things easy for us. Remember, the basis, a set of vectors is going to be a basis if they are going to be linearly independent and if they are going to be span the vector space. This next one would be useful when we want to prove the, when we want to get the dimension or proving the set of vectors is going to be linear independent. And that is going to be the case. Suppose you have a vector space. Okay, suppose V is a vector space. V is a vector space. Okay, V is going to be a vector space. V is going to be a vector space of dimension n. Of dimension, okay, dimension n. Dimension n means any basis would have n vectors. That's going to be the one. So that makes things easy for us. You see, if this is going to be the case, then part one. If you have, okay, if you have a set of vectors, okay, if it's going to be a set of vector, we call it S. If S would have a V1, V2, up to the Vn, if this is going to be a set of linear independent vector, is a set of, okay, set of n linearly independent, okay, linearly independent vectors in V, automatically that would be a basis. Then, okay, S is a basis. It's going to be a basis for V. You know that to be a basis, you have to prove two conditions. One condition is going to be linearly independent. The other condition is that they must span, okay? You have to prove that each vector is going to be linear combination of the, okay, of these, the one on the, okay, in your base. But if you already got the dimension n, okay, since the dimension is n, so this means if you get any set of linear independence, okay, if you get any set of linear independence, then that set would span the, okay, that would span the vector space. You don't have to prove the spanning one, okay? Just prove that it's linear independent and you're done. It's the same thing for the spanning sets, but they must have n elements because the dimension is n. Okay, dimension is going to be n. So the second one is going to be if this is going to be the set of V1, V2, up to the Vn. Okay, is going to be, is a set of vector, is a set of vectors with the condition, okay, set of vector such that, okay, is going to be set of vector such that this vector would span, okay, V would be spanned by the, okay, by the vectors in this one. And since the dimension is n, this set is automatically a basis again. So this means you don't have to prove they're now linearly independent. So when the dimension is n, to be linear independent and a spanning subspace, both of them are going to be the same. If you have one of them, you get the other ones. Okay, so is a set of vectors such that V is going to be a span of S, then automatically S is going to be a basis. It's going to be a basis for V. That would be helpful. Okay, I'm not going to prove it. You can check it yourself. That would be helpful. That would be helpful for you if you want to prove that. You see, if this set is given to you, if you want to prove that this is going to be a basis, you have two choices. You may prove that they are linear independent, or you may prove that they are going to be spanning subsets. So you don't have to prove both of them to show that this is going to be a basis. Okay, so give you an example. If we're going to operate with this one, these examples are very important and they are quite a lot is going to be happen. Okay, so there you are. Just applying this theorem. We want to prove that. Okay, prove that this setup basis. Okay, I write the b equal to I have 1, 3, -1. Then I have 2, 1, 0. Then I have 4, 2, 1. I want to prove that this is a basis. Is a basis. Okay, a basis for R3. You see, that's one. We did have this problem before. So what we proved, remember, we proved that this is linear independent. And at the same time, we proved that each vector B in R3 is the linear combination of this. You did it on your previous quiz. But now you use the dimension. If you use the dimension, you see, this is R3. So we know that the dimension of R3 is 3. Okay, so we say, oh, we know this one. Note that the dimension, okay, the dimension of R3 is 3. Since the dimension is 3, you don't have to prove all of them. You need to just prove one fact. If you just prove that they are linearly independent, then you're done. Okay? You don't have to prove the spanning one because you know that you need only 3 vectors. Okay, so since this is going to be the case, okay, yes, therefore, these 3 vectors, if you like, therefore, the set of these 3 vectors, we call it V1, V2, and V3, is going to be, okay, is going to be a basis, for R3 if they are going to be linearly independent. If it is linearly, okay, linearly independent, dependent. And you know that that's easily can be solved. Can we check? Okay, so how we check? Suppose we have C1, C2. Okay, suppose C1, C2, and C3. Okay, suppose C1, C2, C3 are what? Are scalars such that C1V1 plus C2V2 plus C3V3 is equal to the 0. You know that you have to prove that the C1, C2, C3, all of them are going to be equal to the 0. Okay, so as we did it before, you just put them together and you get that matrix of the coefficient. Okay, remember this is going to be what? This is going to be C1, you get 1, 3, -1, plus C2. C2, we get the 2, 1, 0. Then we get the C3, which is 4, 2, 1 equal to what? Is equal to the 0. And if you put them together, that system of the equation that we usually use, remember C1, this is going to be C1 plus 2C2. Okay, 2C2 plus 4C3 equal to the 0, the first component. The second component is a 3C1. Okay, 3C1 plus C2 and plus 2C3 equal to the 0. The third component is a negative C1. Okay, this is 0, and this is just C3 equal to the 0. You can solve it to show that the C1, C2, C3 is equal to the 0, or remember, you can use the matrix of the coefficient, and so that the determinant of a matrix of the coefficient is not 0. So you have two choices. So the first one choice is that the matrix of the coefficient is going to be 1, 2, 4, and the second one is 3, 1, 2, and the last one is going to be negative 1, 0, 3. Okay, if you find the determinant of this matrix, okay, the determinant of the A, if you find that determinant is going to be, it's very easy to find. Okay, so it's going to be equal to, right down here, is going to be equal to just, expand it through this first line. So that give you 1. Okay, it's going to be 1 times 1 minus 2 times, okay, eliminate the row and the column. That give you 3 plus 2. Okay, 3 plus 2 and plus 4. 4 just cross these two, that give you just 4 times 1. Okay, and if you simplify it, that gives us 1 and minus 10 plus 4. So it's going to be negative 5 is not equal to the 0. We know that if this matrix is not going to be 0, so that gives you C1, C2, C3 equal to the 0, and then you're done. Okay, so since you know that the dimension is 3, so this is going to be a basis if only they are linearly independent. To prove that it's going to be linear independent, you get a scalar multiplication, a scalar combination of the C1, C2, linear combination of C1, C2, C1, V1, C2, V2, C3, V2 equals 0, and you prove that the C1, C2, and C3 are 0. So you can solve this system to show that they are 0, or you can consider the matrix of the coefficient and prove that the determinant of the matrix is not equal to 0. Remember, we did this one before. So this is one advantage of this theorem. Okay, give you another one. So get to know this type of proofs. So the other one is going to be, give you an example with the polynomial type. So this is going to be the next example. Okay, so what is going to be the next example? We want to give you a basis again. Okay, we want to determine, okay, determine if this is whether, okay, this set of the, we call it S, equal to, it's a 1 minus x, okay, comma, 2 minus 3x squared, okay, comma, and that gives us x plus, okay, x plus 2x squared again, okay. So this is going to be the case. We want to check to see if this is going to be a basis. Is going to be a basis. Okay, a basis for what? For P2. Remember, P2 is what? Is of polynomials with degree at most 2. Okay, of it's going to be polynomials of degree. Okay, of degree less than or equal to 2. Okay, we want to know if this is going to be a basis. Okay, now again, we know that we already talked about it. The dimension of P2 is equal to 3. Remember, it's a polynomial. If it's going to be n, you get n plus 1. So again, if you have a set of 3 vectors, that set would be a basis if they are going to be linearly independent again. Okay, so this is going to be the solution. Then you explain it, note that the dimension, okay, the dimension of P2 is equal to 3. You know that because 1x and x squared is a base. Okay, just remind you that 1x and x squared is a basis. You know, we talked about it before. I just remind you, a basis for P2. Okay, so this means you need 3 vectors. So you have to prove again that this is going to be linearly independent. Okay, so this is going to be the case. So one math, if you like, show that S is linearly independent. Okay, again, the same case, same thing. Get those scalars. So suppose C1, C2, and C3 are going to be scalars with, as usual, C1 V1, C2 V2, and the C3 V3 is equal to the 0. Okay, go and format. So we have the C1 times the vector 1 minus x plus C2 times, okay, 2 minus 3x squared, and plus C3 times x plus 2x squared. We did a similar one even on your test. Okay, this is it. You are going to distribute it and simplify it. Okay, if you multiply them together, the constant term would be C1 from here and the 2C2. Okay, that's going to be the constant term. Then the x's are going to be, okay, negative C1 plus C3 times x, okay, and the other one is going to be, what's that? It's a negative 3C2 plus 2C3, okay, times the x squared. Okay, so it's going to be times x squared equal to the 0. So you form a system of the equation, and this is going to be C1 plus 2C2 equal to the 0, negative C1 plus C3 equal to the 0, and the last one would be negative 3C2 plus 2C3 equal to the 0. Okay, you can use a matrices, okay, again, or just solve it directly, really. It's very easy to solve directly. Okay, to show that, it's directly can be solved. C1 equal to the C2 equal to the C3 equal to the 0. Okay, if you want to check the matrix of the coefficient, you see this is going to be a matrix of the coefficient again. So the first one is going to be 1, 2, 0. The second one is going to be negative 1, 0, 1. And the last one is going to be 0, negative 3, and 2. So it's going to be your matrix. You find the determinant of this matrix. So the det of A is going to be, okay, it can be seen easily that it's not going to be 0, okay? it's going to be 1. So that give you 3. That give you a -2 times eliminate the first row, and that give you this would give you easily a -2 minus 0, -2. Okay, so that give you 3 plus 4 is equal to the 7, and the 7 is not equal to the 0. Okay, so this, you know that anytime this matrix is going to be invertible, then the solution to this system is going to be 0, 0, 0. Remember, ax equal to the b is equal to the 0, and you find the a inverse, and that gives you the final answer. Okay, so this is going to be the case. So these are one action that the set would be given to you, and then you just prove it is going to be a basis. Now you have one tricky problem, if you like, in your book regarding these type of problems. Okay, so I explained that one for you. This is it. So look at this example. To explain it, X example. So in this example, what we want to prove is we want to find a basis. You see, that's it. It's kind of different from the other problems, but it would be fine. So what we would like to do, we'd like you to find a basis. Okay, find a basis. Find the basis for the vector space. For the vector space P3. You know that the P3, the dimension is 4, 3 plus 1. So you need 4 vectors containing, containing the following vectors, the polynomials. The polynomials. Okay, the polynomials x squared plus 1 and x squared minus 1. It's something which is different. Just want to make sure you know it. Okay, so what's going to be the idea of these type of problems? Okay, it's a very unique problem. So we know that the dimension of the P3 is 4. So you need 4 vectors. You already got 2. So you need 2 more, okay, to add them together. So I'm going to bring those 2 more. So just to remind you that what are going to be the standard base for this one. So the solution is going to be, you start with this fact that, note that, you must know this. Okay, note that the dimension, okay, the dimension of P3 is equal to 4. What is the base? And you see, and this is going to be the case, and 1 x squared x3 is going to be what? Is a basis. Is the basis for P3. So what do you want to do? Okay, so the question is going to be, what you want to do is going to be, this is what you want to do. So one can find, if you like, one can or should find, okay, this is going to be this set. You already got the x squared plus 1. And then you have x squared minus 1. Okay, so you need 2 more vectors. You see? 2 more vectors to find whether this is going to be, one should find, this one has a basis, if you like, as a basis for, for P3. So what's going to be the possibilities? You know that x squared plus 1 and x squared minus 1, they are, okay, they are linearly independent. So one of them is not a scalar multiplication, okay, second, a scalar multiple of the other one. So they are independent, okay? So you note that x squared plus 1 and x squared minus 1 are not a scalar multiple of each other. You know that when you have two vectors, they are going to be linearly dependent if one of them is not a scalar multiple of the other one. So are not a scalar, okay, a scalar multiplication of each other, and so, okay, and so are linearly independent. So what you are going to do is, you see, you go to the, you see, this is the one that you have, 1x, x squared, and x cubed. So two of these would be the one that you put them over here, and then you get your vectors. So just check to see which of these can join here. Okay, which of these can join here to get these numbers. You start with the 1. If you put the 1 as the member of this group, these vectors must be linearly independent. Okay, but 1 is what? 1 is going to be the, okay, the difference of these two, if you like. Difference of these two would be 2. So 2 is, okay, 1 times 2. So you cannot do the 1 here. Okay. Then you just check another one. Okay. So check the x squared. You cannot have the x squared here, because x squared is a linear combination of the other two. Because if you add these two together, that give you 1 and 1 disappear, that give x squared. So we cannot join the 1. We cannot join the x squared. So we can join x and x cubed. If you put the x and x cubed here, you get 1, 2, 3, 4. So that give you the 1. Okay, so what we are going to do is, we are going to check, okay, to check which of these vectors are going to be a good one for us to get these numbers. Okay, so we note that 1 and x squared, 1 and x squared are linear combination of these two vectors that you have. A combination of what? Of x squared plus 1 and x squared minus 1. So we cannot put them over here. Okay, it can be easily seen. You see, it can be easily seen that, you know, you get there. If you want to get the 1, for example, you don't have to write down. You see, 1 is what? Is 1/2 of x squared plus 1. Okay, and plus 1/2 minus 1/2 of x squared minus 1. If you distribute it, that gives you exactly 1. Because these two would cancel out. We see 1/2 of x squared and negative 1/2 of x squared would cancel out. That gives you a positive 1/2, and the, okay, and positive 1/2 would be 1. And the x squared is the same thing. So x squared, if you subtract these two, that give you x squared. Yes. If you subtract it, so that's going to be x squared. Okay. To get this number, it's going to be a linear combination of these two again. Okay. So that give you, so the x squared would be out, because it's a linear combination. You know, we can write it. What's that? It's going to be x squared. Okay. It's going to be simply you already got the x squared. It's going to be x squared plus 1 if you like. Okay, and this is going to be minus x squared. Okay, it's going to be, in fact, plus would be fine. You see, if you add them together, if you add them together, the 1 and 1 disappear, so they give it 2x squared. Okay, so it's going to be plus. It's a 1/2, and this is going to be 1/2. Okay, because if you distribute it, so that give you what? It's a 1/2 of x squared plus 1/2, and this is going to be 1/2 of x squared minus 1/2. So this would cancel out, that give you x squared. It's the same thing for the first one. Okay, so 1 and 1x squared are a linear combination of x squared plus 1 and x squared minus 1, so you cannot join here. But the other two are fine. Okay, so this is it. So therefore, you see, the other two are not. Therefore, if you are going to get the x squared plus 1, you see this is x squared plus 1. This is x squared minus 1. Then what you do is you join the other two here. You join the x and you join the x cubed. See, because x is not a linear combination of these two or x cubed. So this is going to be a basis. A basis for, okay, for P3. Okay, it's just a unique problem. This is from your book. I just want to make sure that you know how to take care of these type of problems. Okay, so that's the idea, and the important part is the dimension. You see, you know that since the dimension of the P3 is 4, so you know that there is a standard basis. This is a standard basis. You want to create a new one yourself, but you want to create one that contains these two vectors. You need 4 vectors. So we already got the 2. So how about the other 2? So we can borrow from this one. Okay, we borrowed from this one, but we want to make sure that the vector is going to be linearly independent. We cannot borrow the 1 and the x squared, because 1 can be a linear combination of x squared plus 1 and x squared minus 1. And the x squared is the same thing. But we can borrow these two, because you cannot write x as a linear combination of these two because the power are different. You cannot write x cubed, so that power would be different. Okay, so that gives you the idea. Okay, in case okay, so in case you want to, okay, to get these numbers. Okay, so this is going to be the case that we're going to have. Now, there are some other groups of the problems, okay, and very important one. You see, the one that I talked about, it, there was just, you know, the vectors was given to you, just check. But there are going to be some subspaces. Remember, we talk about the subspace. The dimension of a subspace is going to be less than equal to the dimension of the full space. Okay, so some subspaces would be given to you, and they ask you to find the dimension. It's very important one. And there is a trick that I'm going to show you to get this type of problems quickly. So this is it. Example. So this is going to be dimension of the, okay, finding. Okay, finding the dimension of a subspace. Of a subspace. Remember, you have to provide a base to be able to find that. So let's try to see what is going to be the involved, you know, these type of problems. So this is it. You get the message for this one. So suppose, okay, suppose U and V, U and W, if you like, U and W are going to be the following. Are going to be the following subspaces okay, following subspaces of R4. Okay, following subspace of R4. So this is it. The first one, U is equal to, okay, U is equal to the all the elements A, B, C, D, with this condition that the B plus C plus D is equal to the 0. That is U. Okay, all the vectors with this condition. What's going to be W? W is going to be what? W is going to be all the members A, B, C, D, with the condition that A plus B is equal to the 0 and C is equal to the 2D. Okay, so what do you want? You want to find the dimension. Okay, find the dimension of each space, the dimension of each subspace, dimension, and a basis, of course. A basis for U and W. You know that when you want to find the dimension, you have to find the base. If you find a basis for U, okay, or for W, the number of the vectors in that base is going to be your dimension. Okay, so how are we going to find those? You see, remember, we have two cases that we know we can use it. The dimension of the R4 is 4. So the possibility for the dimension of U is going to be 0, 1, 2, 3, 4. So this is going to be the possibilities. So what we're going to do is, remember, definition is going to be, you are going to find a set of vectors that span the U. Okay, so this means you find a set of vectors in which each of the members of the U is going to be a linear combination of those. If you can find that, you're done. Then that gives you automatically the basis and the dimension. So how are we going to find it? You see, you have to take care of this to find the relationship between, you have to find the A, B, C, D. Okay, so in this, if you want to identify a member of U, you need what? A, B, C, D. There are 4 unknown. So you want to find the 4 unknown. So what do you have? You have only one equation. You know that you have one equation, but you have 4 unknowns. And you know what does it mean? This means if you want to find it, okay, this equation will give you the answer for one of them only. So all the other 3 must be a free one. Remember, because you have fewer equations that your unknowns. So this is how we're going to set up the problem. There is one way in your book. They ask you to check 0, 1, 0, 1, 0, 1. Not going to be a very good one when things getting complicated. So this method is much, much better. Okay, and you are going to see it quite a lot. So the solution is going to be, I'll go with the U first. Okay, so I have the U. U is A, B, C, D. I'm going to find a spanning subset for you. Spanning vectors. So work on this one first. Okay, work on this one first. Okay, so what we are going to do is, so one should find, if you like, one should find a basis. Okay, a basis. Okay, for the solutions. Okay, for the solution A, B, C, and D of the following equation. Okay, of the following equation. Okay, following equation. So what is your equation? So your equation is what? Your equation is B plus C plus D equal to the 0. Okay, B plus C equal to the 0. So what you can do is, as I told you, you have one equation for variables. So you have to pick three of the variables to be free. Okay, so note that we have we have three, if you like, three free variables, if you like, free variables. So for example, you can pick the A to be free. Free means can be any number, you call it T. Get the B to be free variables like a S. Okay, then pick the C to be free. C is U. Okay, so 1, 2, 3. Now go and find the fourth one. Okay, if you pick this one, so what you need is you need the D. So go from this equation, substitute. Okay, so that gives you S plus U is equal to the D. That's it. Sorry, is plus D equal to the 0. So your D would be what? D would be negative S minus U. Okay, so you have the solution. So what is your solution? So this means the solution of a system is what? A, B, C, D is equal to, what is A? T. What is B? S. What is C? U. What is D? Minus negative S minus U. It's going to be the case for any real numbers. Any real numbers, if you like. The real numbers are going to be what? S, T, and U. You see, this is going to be your set of solutions. So this basically means that your space, you see, your space, which was U, is equal to what? Your space is going to be equal to these type of members. It's going to be T, S, U, negative S minus U, when S, T, U are numbers, are in R, if you like. This is your space. Okay, now you can easily find the basis. How are we going to find it? Write this one as a linear combination of some easy vectors, 0, 1, 0, 1, 0, 1, 0, 1. So this is the way you can do it quickly. You see, this is my method. Okay, I have the T, S, comma, U, comma, negative S minus U. I'm going to write it as a linear combination of some easy vector. You see the way we are going to do it, we start with this variable T. So you pull out the T. Okay, you pull out the T. The way you are going to pull out the T, this means when you go to this one, so this means you like the T, but you don't like any other one. So this means you are going to replace the T by 1, okay? You are going to replace the T by 1, everything else by, okay, everything else by 0. So if you replace everything else by 0, so that give you what? 0, 0, 0. That's the first one. Then you are going to add it to the S. So this means you are interested in S. Replace S by 1, everything else by 0. So that gives you 0, 0, 1, 0. U would be 0, but S is 1, so that gives you negative 1. You see? Then you pull out the U out. So you are interested in U. Replace the U by 1, anything else by 0. So that gives you 0, 0, 1. Okay, 1, 0. That's it. You see, if you add these together, then you will exactly the same thing. You see, T equal to 1, the first component of 0. So that gives you T. The next one, the second component. You see, this is 0, but you get the S only here. You get the S. The third component, you get the 0, 0, but you get the U. And automatically you get, you get the other ones. So as you can see, these three vectors, you can look at this one. 1, 2, 3. Any member, you can write any member of your set as the linear combination of these three vectors. This is a spanning subspace, remember? So this is going to be linearly independent one. So this means B equal to, okay, B equal to the 1, 0, 0, 0, okay, 0, 1, 0, negative 1, 0, 0, 1, 0 is a basis. Okay, it's going to be a basis for U, and so the dimension of U is 3. Very nice method. Okay, and would be so useful for us, okay, to get these type of ideas. In your book, they give you this 0, 0, 0 by chance, just check it at the beginning. But this method is much, much better. Okay, so you solve whatever you have, because the condition was B plus C plus D equal to the 0. So you have to solve this equation to get A, B, C, D. You can't do it. You have one equation, 4 variables. So 3 variables must be free. I get the A, B, C to be T, S, U. Later on, you find out that as soon as you have 3 free variables, this means the dimension is 3. But not now. We ask you for the basis. That's why. See, we ask you for the basis, so you have to go through it right through the end. Okay, so you put them together, then you have to break this one into the linear combination of some vectors. The way you break it, for each variable, you pull it out if you like. When you pull it out, you replace, anytime you see the T, you replace it by 1. Anywhere else is 0. Okay, then you pull out the U and you continue. If you can do it with 3 vectors, means the dimension is 3. If you can do it with 2 vectors, the dimension would be 2. Okay, so I'm going to do the W for you to see the difference. You see, look at the W. You have 2 equations this time. So you're going to have 2 free variables. So the dimension would be 2. But you have to give us basis. Okay, so let's check the second part. It's very nice method. Okay, very useful. You'll see in a minute in more complicated cases. So what's going to be the W? You see, this is W, A, B, C, D, with the condition that A plus B is equal to the 0. Okay, and the C equal to the 2D. So as I did it for the other one, I'm not going to explain this one anymore. You see, this is it. You have A plus B equal to the 0, and you have a C equal to 2D. Okay, C equal to the 2D for this equation that you have. So you cannot solve it because you need 2 free variables, because you have 4. You see, 1, 2, 3, 4. You have to equation, so you have to pick 2 of these to be free. So you can, if you like, write the first one as A equal to the negative B, and C is equal to the negative 2D. So you can pick, that's a choice. If you pick something for the B, then you'll be able to find the A. And if you pick something for the D, you'll be able to find the C. Okay, so you're going to suppose it's one option. Suppose B is equal to the, okay, B is equal to the S, for example, and D is equal to T. If this is going to be the case, then your A is a negative B, now it's going to be negative S, and your C, which is a 2D, is going to be 2T. Okay, so you have a solution. So what's going to be your W now? Okay, so you have the A, B, C, D. Now it's going to be A. What is the A? A is a negative S. What is B? B is S. Okay, what is C? C is 2T, and the D is T. Okay, so your W is what? So the W will be of this format, of the form of a negative S, S, 2T, T. When we have 2 variables when S and T are numbers, are in R. Okay, so you should be able to expand this subspace with two vectors. So you have to show us, you see this is the way we do it. You need a base, negative S, S, 2T, T. Okay, 2T, bracket is going to be equal to, you pull out the S, so you like S. If you like S, you replace the S by 1, negative 1, 1. But the T by 0. Okay, because you need to have a negative S and S. Now you pull out the T, it means you like T, you replace the T by 1, S by 0. So that gives you 0, 0, 2, 1. That's it. You see, if you can double check it. If you put them together, that the first component gives you negative S, the second component gives you 1, the third component nothing here, but we get a 2T, and the last component nothing here, but we get a T. That's it. So each member of the W can be written as a linear combination of two vectors. So B equal to, okay, B equal to negative 1, 1, 0, 0, comma, okay, 0, 0, 2, 1 is the basis. Okay, it's going to be a basis for W. So the dimension of the W is 2, because you can create it by using a space of two vectors. Okay, and we get quite a lot of these type of problems in your next practice one, in your test, okay, and in your book. So that gives you the idea of these subspaces. Okay, there is one more example. I try to give you this one next time. Actually, I give you another recording. The other one is you're given a system of equation. Remember, when you solve a system of the equation, you may have one solution, no solution, or infinity many solutions. When it's infinity many solutions, the subspace, if you put all those solutions in one space, that space is going to be a vector space. So we would like to find what is the dimension of those. That would be very useful for us, okay, in future. So you'll be given a system of the equation. You solve it, the system would have infinity many solutions. You know that when it's infinity solution, the solution would be of this format because you have some free variables. So your job is a little bit more, more, because you have to solve the system. Okay, in this one was easy because a couple of them was missing. So we give you a system of the equation. You have to put it into the matrix form, do the row echelon form a couple of times, so that that will take you into the into this format. Okay, I think that would be too much. I talk about it probably by Friday. I give you another one. So it's very important sections. I give you more examples. Very important one. This section. Okay, that was 4.4.5. We are not done. And then again, another tricky section is a 4.6. I try to give you these two by the end of this week. I know that next week you are going to have a break. Okay, so we can work on these two section, which is a little bit tricky. The other section is going to be straightforward, but it needs practice this one. Okay, I post this one. Have a good one. And then I give you another one soon. Okay, more examples and that idea of the next section. The next section is something we call it change of base formula. And that's going to be used in geometry. So it's not difficult, but to understand it, it's going to be takes a little bit of time. But we are going to do it, nothing to worry about. Okay, read these examples. If you have any question, let me know. Okay, have a good one. Take care. So I'll probably give you another one on Friday after my classes, so that during the break you get enough time to to get these two sections. You get many problems in your book. And let me know if you have any difficulty for these problems. Okay, have a good one. Take care.